All right, so first of all, we're going to take a look today at section 8.4, trigonometric substitutions. And there are three basic substitutions, and I'm going to show you where they came from. Not because I expect you to have to derive where they came from, but I don't want you to figure out or feel like they just sort of appeared out of nowhere. They're actually coming from right triangle trigonometry. I'm going to show you how to think about it from an analytical, that means like an algebraic point of view for the substitution, and also from a geometric, which is the right triangle point of view from the substitution. Okay, so we're going to look at it from both angles, and hopefully we'll hit most of you on the understanding of where these items are coming from. Okay, so this method is going to be used to evaluate integrals that involve radicals that are a squared minus u squared plus u squared, and u squared minus a squared. So anytime we see our substitutions where it has those forms, it's going to be a trigonometric substitution. So this is the red flag part. The objective in doing these is to eliminate the radical by using Pythagorean identities. And the Pythagorean identities that we're referencing are the trigonometric Pythagorean identities, right? Like sine squared plus cosine squared equals 1. And then we had one for tangent and secant, and we had one for cotangent and cosecant. Y'all remember what I'm talking about? Okay, so those are the three Pythagorean identities that it's referencing on what we're going to be using to eliminate these things. There are three of these that are listed here, and there are three different substitutions that are going to associate with them. And we all talked about last time, I'm not asking you to memorize these, but as you're sort of thinking through bulleted list of things that I don't want to have to go researching as I'm looking on my test because it's open note, open book, this might be one of those list of things on there, right? In fact, it probably will. So here's the first one, a squared minus u squared. And what we're going to do with this is we're going to let the u substitution be a sine theta. I'm going to show you why that's helpful, okay, in terms of an analytic or how that works in an analytic point of view, and then we'll do the geometric. So let's actually do the substitution and see what happens. So in other words, we're going to plug in into the a squared minus u squared. We're going to plug in u is equal to a sine of theta. Okay, so we've still got the a squared, but in place of u, we're going to put in a sine of theta squared. And we're going to clean this up and simplify this. So no problem. So what happens when we do this, of course, is we get a squared minus a squared sine squared of theta. Because I have the square root of a squared, I can factor the a squared out and then take the square root of it. So this ends up being an a on the outside and a 1 minus sine squared underneath. And what is 1 minus sine squared? Cosine squared. And then we're going to take the square root, so we're going to get cosine. And this works for negative pi halves for theta to pi halves. Hang on. Because we're kind of taking the square root. We're doing a lot of weird things with square roots, right? We're taking the square root several different places here, and we're just sort of ignoring the fact that the pluses or minuses are appearing at different spots. Y'all know what I'm talking about? Right? So we have to be a little bit careful. So this is the condition that will keep us a little bit careful. So what this does is by letting the u equal a sine of theta, the radical a squared minus u squared becomes a cosine theta. It eliminated the radical and it turned it into a trig function instead. Okay? And I know I haven't showed you how we're going to use this, but this is the substitution that we will use. I want to show it to you from a triangle perspective, though, as well. Okay, so pretend like that's a right triangle. It's not super convincing, but pretend. And we have our angle theta in the triangle right here. And the relationship that we are establishing is written right here. U is equal to a sine of theta. And if you'll remember from trigonometry, sine of theta, using that relationship, would then be u over a, right, from here. Sine of theta is u over a. And then from our triangle, if we have the sine of theta, sine is what in terms of opposite of hypotenuse? So the opposite would be u, which would be here. The hypotenuse would be a, which would be here. So far, so good? Okay, so we want to find the third side of our triangle. And if you take a look at the third side of the triangle, you're going to end up seeing a very familiar looking piece of information come through. So it should be, using Pythagorean formula, we should have this. What did you tell me it was? the square root of a squared minus u squared. Do you see a square root of a squared minus u squared on the screen? Yeah, absolutely. That's the whole point, was that we were trying to get rid of this awkward square root, and we actually have it in our triangle now. And the relationship that establishes the other piece of this information would be cosine. So if you were to use the cosine of theta, then you would get this interesting radical, a squared minus u squared, over the hypotenuse, which is a. And if you were to multiply by the hypotenuse to the other side, then we would have that the square root of a squared minus u squared is in fact a cosine of theta. So both from an analytical point of view, we got to the point where we said a cosine theta, and from a geometric point of view, we got to the point where that radical is equal to a cosine of theta. Okay? So that's where these are coming from. The important thing to remember is the u substitution that's highlighted in blue here, and that the radical ends up equaling a cosine of theta. Those are the two pieces of information you need to take away from this argument right here, is that we proved it twice, two different ways, right? And those are the two pieces of information we need to remember or be able to have access to. We're going to do the same thing for the next one, which has the value where they're added together underneath the radical. Okay? So we're going to try the same thing. We're going to replace the a squared plus u squared. With the a squared plus u squared, we're going to replace the u with a tangent theta. So I've got a squared plus a tangent of theta squared, which gives me a squared plus a squared tangent squared of theta. I can factor the a squared out of both pieces, and then I can pull it out from underneath the radical as a. And then I've got the square root of 1 plus tangent squared of theta, which is secant squared. So now I've got the square root of secant squared of theta, and what's the square root of secant squared? Secant. And again, the condition here, and we don't have to worry too much about these conditions. The only time we'll have to be careful a little bit of them is when we're working with, sorry, I didn't mean to have parentheses there, when we're working with definite integrals, because they'll have actual numerical values for our angle measurements, potentially, or for our sines, or for our variables, excuse me. So our angle has to be between pi over 2 and negative pi over 2 and pi over 2. So again, the two pieces of information from the screen that are useful and valuable to remember are actually these two pieces. U is equal to a tangent of theta, and the square root of a squared plus u squared is a secant squared, or a secant theta. Okay, again, let's look at it from a triangle point of view. Still not a very convincing right triangle. Man. All right, here's theta. The relationship is about tangent, and if I reorder this right here, this tells me that the tangent of theta should be u over a. So where do the u and the a go on my triangle? Opposite and adjacent. And what do I get then for the third side, my hypotenuse? Right, square root of a squared plus u squared, or u squared plus a squared, either way. Okay? And the relationship that we're establishing compares these three pieces of information. It's always comparing the constant, because a is a constant, to the other piece that has the radical involved. We don't want the u involved, okay? We want the constant a and the radical involved. So what relationship relates these three quantities together? Usually we would say cosine, right? Okay, so if I were to say cosine, take a look here. Cosine of theta then would be the adjacent, which is a, over the square root, which is a squared plus u squared. That's how I usually would think about this picture, correct? But that puts the variable in the denominator, which isn't very friendly for working with it. So instead of having my variable in the denominator, if I flip this upside down so that I have the square root of a squared plus u squared over a, what trig identity is the reciprocal of cosine? Secant. So I have secant of theta, and I can multiply the a to the other side. A secant of theta equals the radical a squared plus u squared from a geometric description. Okay, and we have one more. The one more that we have takes the very first one, which was a squared minus u squared, and it flips it, so now it's u squared minus a squared. And you might feel like, well, it shouldn't be that different because it's just, different by a negative, but it's a negative underneath the radical, so things do end up being a little bit different. You'll notice the u substitution that we're identified here is a secant theta. So we're going to take u squared minus a squared, and we're going to replace the u with a secant of theta. That will be squared minus the a squared. So as we simplify that, I have a squared secant squared of theta minus a squared. I can do the same thing I've been doing with my a's by factoring them out and then pulling them out of the radical. I end up with secant squared of theta minus 1, which is tangent squared. And of course the square root of tangent squared would be tangent. And that works as long as my angle, hang on, I've got one more thing to add in here, has certain features. So this actually gives me two values. We have to be careful on this one. The first one happens when the u value is bigger than a, and the second value happens when the u value is less than negative a. Now you have to go back up and you have to think about this angle, or not angle, but this radicand, the value underneath the radical. This is only going to work as long as the u squared is bigger than a squared, correct? I need a positive value underneath there, otherwise I don't end up actually having a value in a real number system, and I need a real number system because we're working with calculus and real numbers. So the question then is, where is u squared greater than a squared? Well, the simplest thing to sort of describe that as is to actually have left it on the other side. So if I had left this where this is greater than 0 and I factored it, so let me move this over just a little bit. If I factor that, I get u minus a and I get u plus a. Whoops, it's greater than 0. And I would set up a number line. That's what I would do. This is like a calculus, or not calculus, a college algebra concept. We'd have negative a and positive a here, and we'd test the different intervals. And we would find out that it's positive here, negative here, and positive here by testing values. So the only values that will work are values where I have a positive underneath the radical, which is these two end points, or in these two sides of my interval. So that's when we specifically have u less than negative a and u greater than positive a. So that's what's going on at the end of this particular problem. We still have our consideration on our angle. Our angle this time, because we're dealing with tangent, actually ends up being slightly different. Our angle is between 0 and pi over 2. And it's also between negative pi over, I'm sorry, I hit that on the wrong side, pi over 2 and pi. So why is this not just say that I can go from 0 to pi? Any ideas? Nope, it's something more trig related than that idea. Yeah, we got to exclude the pi over 2 value because we happen to have an asymptote with tangent there. So that's why that's excluded instead of just being an all-encompassing interval. And we didn't have that happen with the last two. All right, this one or with this one, we didn't have to worry about those features because the asymptotes weren't occurring in between there. Okay, sorry, one more time. We're going to do this with a triangle. Okay, so I've got my third attempt at drawing a right triangle. I don't expect it to go well. Yep, pretty much like the last two times. It's a little bit on an angle. It's not perpendicular, but pretend. All right, so here's my theta. I've got this relationship set up over here. So again, if I change this, I would say secant of theta would equal u over a. Okay, so I've got the angle theta. Secant, what would secant be in terms of a right triangle? Hypotenuse over adjacent. It's just like cosine but reciprocated, right? So cosine is adjacent over hypotenuse. So secant would be hypotenuse, so this is my u, over adjacent, which would be my a. Okay. And then what would I do for the third side of my triangle? I'm going to have a radical. What else am I going to have? Yep, there's that u squared minus a squared that we were looking for, right? Cool. So now we have to have a relationship between these two pieces of information because it's one side is the constant, the other side is the radical information. And what relationship exists between those two? Don't everybody talk at once. Which trig function is it? Tangent. Tangent of theta is the opposite, which is this radical, u squared minus a squared, over the adjacent, which is going to be the a. And it's plus or minus a because the triangle will be drawn in different quadrants potentially. So if it's drawn in quadrant 1, we'd be at positive a. If we drew this triangle in quadrant 2, we'd actually have a negative value. So if I take this and I simplify this, I would get that u squared minus a squared underneath the radical on the right, and I would have plus or minus a tangent of theta on the left from a graphical standpoint. Okay. All right, so like I said, I don't have any intention or a plan, or it won't happen, so to speak, that I'm going to ask you to repeat this process or anything like that. But I do want you to see that they do come from somewhere, these values and these substitutions that we're making. And I didn't highlight the last one at the end here, but this one is that the square root of u squared minus a squared gets replaced by one of those two values. Okay, either positive or negative a tangent of theta. So let's see how this actually plays out in terms of a problem. So looking at this problem, what is it about this problem that says I'm going to use trig substitution to you? We have a square root of a variable and a constant, and they both appear squared, correct? Like 16 is something squared, x squared is something squared. Good. Which one is it? Okay, so we have a squared minus u squared. Oh goodness, what happened here? It's this piece right here. It's the first one because our constant came first, our variable came second. So what does that mean our substitution is going to be? A sine of theta. And that's the substitution for u, and the substitution for the square root part will be a cosine theta, right? Okay, so I'm going to write down both of those substitutions because we're going to need both of those pieces of information as we're working. We are deciding right now that the substitution for our variable, and our variable is x, is going to be a, which is 4, I should identify that too, 4 sine of theta, right? And we've also identified that the square root of the 16 minus x squared is going to be a, which is 4 cosine of theta. That's what we've established thus far on the previous slides. Now, every time you make a substitution, though, you change variables, you have to have the substitution for the integral, or the integrand at the end, right? The dx part of this. I need to know if x is 4 sine theta, what is dx? What is it? What is the derivative of 4 sine theta? 4 cosine theta. See, here's the catch. I need to replace all three pieces of this information. I know how I'm going to replace the top. It's 4 cosine theta. I know I'm going to replace the bottom. It's 4 sine theta. And I need to know how I'm going to replace the dx. So I need to figure out what dx is in terms of this new variable that I've introduced, theta. So dx in terms of x equals 4 sine theta is 4 cosine theta. So I'm going to be making 3 substitutions in this problem. I've got my integral. The substitution on top was 4 cosine theta. The substitution on bottom is 4 sine of theta. And the substitution for the dx is also 4 cosine of theta, d theta. Sorry, I left that off over here. Let me put that in. The derivative of 4 sine theta is 4 cosine theta d theta. Well, we need to clean that up and figure out what we're going to do based on what you just did in section 8.3. So let's take a look. We now have the integral of, well, let's see. Hang on, what do I want to do? I can cancel these 4's out, so there's only one 4, right? So I have a 4. I have cosine squared of theta over the sine of theta d theta. Is everybody good with that so far? Fabulous. In the last section, you figured out, and we learned and we talked through what happens when exponents happen on trig functions. This is a cosine squared. When you have cosine squared or you have sine squared and no other powers are present in the function, we had something called a power reducing formula. Do you guys remember that? We also had the Pythagorean identity, right? It says sine squared plus cosine squared equals 1. So those are our two sort of places to go if we needed to reduce this power, to change this power into something else. Pythagorean identity is usually quite friendly when it works, and it's a good place to start to see if it's going to. So if I use the Pythagorean identity on top, what could I replace cosine squared with? What was it? You're close. 1 minus sine squared theta. Okay, is everybody good with that? That's Pythagorean identity. Sine squared plus cosine squared equals 1. So cosine squared is 1 minus sine squared. The beautiful thing with having addition and subtraction on top is that you can actually divide each of the pieces that are on top by the denominator. So we've got 1 over sine theta, and we've got sine squared over sine theta. And if we treat them like a fraction, then we can actually simplify them in that way as well. So this is 1 over sine of theta, and the other piece is sine squared of theta over sine of theta. So let's use a little bit of trig to simplify that. Cosecant of theta on the first piece minus sine of theta on the second one. Okay, we could take the derivative, the antiderivative, or the integral of each of those pieces. So do you remember what the antiderivative of cosecant of theta is? It's a natural log. It's actually a negative natural log. And I'll let you cheat a little bit while I write down what's on my paper, of cosecant of theta, plus cotangent of theta. Very good. You guys remember. Wonderful. Plus, what's the antiderivative of negative sine? Or what's the antiderivative of sine, either way? Cosine. And it's going to be positive, right, because there's a negative already there. So then this is plus cosine of theta. Yeah, it has a plus c on the end, and I'm running out of space, so let me move mine over so I can get that plus c there. Okay, somewhere along the way, you had a Calc 1 teacher. Some of you it was me, some of you it wasn't. And they said something has to happen at this point. You're not done. Why not? Yeah, there's the 4 that we got to contend with. I'm not terribly concerned about that, but there's something else more significant that we still have to do. What was the title of this section of this chapter? Substitution, right? What's the other type of substitution we've done so far? Had a name from Calc 1. U substitution. We did U substitution. We have trigonometric substitution. Okay, so let me simplify what you're saying to be a more general phrase instead. We need our problem back in terms of x, right? We changed things into thetas. With U substitution, you change it into u's, right? We changed things into thetas. We can't leave the answer in terms of theta because we created the theta in the problem. We need to turn it back into the problem as it began, which was in terms of x. Now, the beautiful thing is that we have a relationship that we can use for pieces of this, right? We know that x is the same as 4 sine theta. We know that the 4 cosine theta is the same as the radical part. So if we have sines or cosines, that's something we can deal with. The other thing that we can do is that we can actually create the triangle that sets this up. And I think that's probably the most useful fact because not everything in this particular problem, hey, look, I got a right triangle really this time. Like it really worked. Apparently 4th time's the charm today. We have the cosine theta, so that's cool. But we do not have a cotangent or a cosecant written on this triangle so far or on our list of details so far that are highlighted in blue, right? Okay, so let's set up the triangle as it's identified. Well, we know that if we set up the theta, I'll put it on the left. Sine is opposite over hypotenuse. And if I take this piece right here and I rewrite it, we can see that the sine of theta is x over 4. So the opposite is x over here, and the hypotenuse is 4 over here. And either using the Pythagorean identity or using what your information you already know about the cosine in this particular problem, the third side is the square root of 16 minus x squared. So setting up this triangle makes filling out, or changing this back into x's infinitely easier. I'm going to move my triangle to the other side, or the other slide. And I'm also going to move our piece that we're trying to change really quickly here to the other slide. Okay, so we need to replace the cosecant theta, the cotangent theta, and the cosine theta. And we've got this 4 to distribute through, as Evan mentioned, and he's right, we are going to distribute that through as well. So I have -4 natural log of cosecant theta. So in this diagram, this triangle, what is cosecant theta going to be? It is 4 over x. Sine is x over 4, so cosecant is 4 over x. Plus, what is cotangent in this triangle? Okay, so square root of 16 minus x squared, right, over the x. All that's an absolute value. And then as we're working, we're distributing the 4 through as well, so then we have 4. What is 4? Well, what is, let me just notice this. It's going to be 4 cosine theta. And we have a relationship for 4 cosine theta. What is 4 cosine theta? Yeah, that's actually one of them that's highlighted, so we can use that without using the triangle if we'd like. That's actually square root of 16 minus x squared. And then all of that is then plus c. These are a little weird, right? We turn things into triangles that had radicals involved, and in the end we turn them back in, and all of a sudden there's a natural log involved. They're a little bit weird. There's really nothing that we can do to change or to simplify what's inside of our natural log. I mean, if you want to write them both over the same x value, you can do that. But there's really nothing that can be cleaned up any. There's nothing that can be simplified. So this version really is as simple as it gets, and it's mighty messy. There was a 4 out front. Do you mean the 4 cosine theta that's highlighted over here? Mm-hmm. Okay. That was what we went through all through these slides. We started with a u substitution of u equals a sine theta, and we actually made that substitution, and in doing so we found out that the square root of that a squared minus u squared was equal to the a cosine theta. So we got it from those trigonometric identities, or not identities, but substitutions that we made earlier. And we're going to do another one again too, huh?
That also how we got x.
Yes. That u is our x. So your u in all of these 3 setting up problems here is the variable x in our particular problem we worked with. Let's try another one, and it might start to sort of piece together a little bit even better. As you take a look at this one, you see on this one that we have, let me flip my page to it, a radical, and it looks like we have something squared plus something else squared, right? Okay, so that radical clues you in on the fact that we're going to do trigonometric substitution. Everybody good so far? Okay, which of the 3 cases are we in? Yeah, the one that involves addition. There was only one of them, right? And it's the second one, or the middle one right here. I've got an a squared plus a u squared. So if I identify that I'm looking at, and I'll identify it, maybe I'll try and write it out a little bit clearer so that everybody sees it a little bit better here. We're looking at an a squared plus a u squared here. What is our, and we're identifying that to be our 4x squared plus 9. So what is our a? 3. What is our u? It's 2x first, okay? I'm just identifying the pieces here is what I'm doing, Abby. So this is the a that we're working with, and this is the u that we're working with. Okay, everybody good so far? Just in terms of comparing pieces together. Now, what that slide told us was that our u value, which is for us 2x, is supposed to equal, oops, one more slide over, a tangent of theta. Okay, so I'm going to write that down. U is equal to a tangent of theta. But we just said that our u value is 2x, and our a value is what? 3. So our relationship based on the trigonometric substitution work that we've already done is that 2x is equal to 3 tangent theta, and it's probably a little bit cleaner for us to write that this is x is equal to 3/2 tangent of theta, right? The other piece of information that we got from that slide, so this was one of them, and the second one was that the radical of a squared plus u squared was equal to what on the other slide? A secant theta? Is everybody good with that? So our radical that we're dealing with that we've identified properly in the pieces was that 4x squared plus 9 is equal to our a, which is 3 secant of theta. Okay, so that's all information just by doing some substitutions with the letters and the variables. The other piece of information that I'm going to need is I'm going to need what dx is, because there's a dx in my problem that needs to be replaced with its equivalent in terms of thetas. So looking at this dx, or this x, equals 3/2 tangent theta, what is the derivative of 3/2 tangent theta? I did the hard part. There's a 3/2. What is it? Right, so the derivative of tangent is secant squared of theta. So the three pieces of information that are most useful to us right now are what is x, what is dx, and what is the radical that we've got. And that takes care of everything that's in that problem. All the pieces of that problem are now there. So I'm going to take this and I'm going to rewrite. I have an integral. The one on top is just fine. X on bottom is supposed to be, x anywhere is supposed to be 3/2 tangent of theta. The radical also happens to be on bottom, is supposed to be 3 secant of theta. And then the dx is supposed to be 3/2 secant squared of theta. Hang on. And there's a d theta that I left off again this time. Man, that's just sloppy notation, that's what that is. Okay, so some cool things happen. Somebody tell me something cool that you see happens. Oh, that's friendly. I don't have any fractions anymore with numbers. What else? Yeah, this secant of theta cancels with one of these secant thetas, right? That's kind of friendly. I still have a 3 on bottom, so let me see what I've got after I clean them up now. I've got a 1/3. I've got an integral. I've still got a secant of theta on top, and I've got a tangent of theta on bottom, d theta. I think those are all my pieces. Does it look like it to you guys? Notice there's no powers on anything. That makes that kind of nice. I don't really like to deal with or want to deal with the powers, right? It also might be friendly for us to then think about, well, if I don't have powers, what could I do? So what is an option that we kind of like, even back in trig, when we're trying to consolidate or clean up a mess of trig functions? Sines and cosines. Change everything to sines and cosines when we can, right? So let's see what happens when we try to do that. So right now I have the 1/3, the integral. I'm going to separate them out just so that I can see them written and change them a little bit easier. I've got a tangent theta and I've got a secant of theta, and I'm going to change them into their sines and cosines. So what is tangent of theta? Sine over cosine, and since it's in the denominator, I could write this as cosine of theta over sine of theta, right? Likewise, I could think of this as the cotangent of theta. So it's cosine of theta over sine of theta. What is secant of theta? Say it louder. 1 over cosine. And what beautiful thing's going to happen next? Cosines are going to cancel. So this leaves me with 1/3 the integral of 1 over sine of theta. Now some of you did some weird stuff when you saw things like 1 over sine theta on your antiderivative quiz that's in my office that most of you haven't completed yet. You can't deal with the sine theta as long as it's in the denominator, right? The answer is no, Dr. Hands, we can't. We can't deal with it there. So what do we have to do instead? Yeah, we have to rewrite this with cosecant theta. So this is 1/3 the integral of the cosecant of theta. Yep, and then what did you say I'm going to do, Evan? Yep, there's going to be a natural log. It's a negative. So the negative natural log of the absolute value of cosecant of theta plus cotangent of theta. And I have a plus c there at the end. I desperately need a triangle. Oh my goodness, there's another right triangle, just perfect. And 2 for 3. No, 2 for 5. I've done 2 right and 3 wrong. How's that? All right, here's my theta. The relationship over here, what did I have? Let's see. 2x equals, so I have tangent theta. I'm sorry, I can't write this down and think of it this way. This is the one I had. Let me write it over here. 2x equals 3 tangent of theta, right? So that means that tangent of theta equals 2x over 3. We'll just set it up with that. So tangent of theta is opposite. So here's my 2x over adjacent. Where is my 3? There is my 3. And then what would I get for my radical here? Yeah, 4x squared plus 9, just like we had written on the other slide. All right, so here's my triangle. What is the cosecant of theta in this triangle? I think that that would be secant, not cosecant.
Oh, secant's opposite side, so you do the 4x squared plus 9.
Yeah, cosecant is the reciprocal of sine, so you would end up with the square root first, because it would be the hypotenuse. So 4x squared plus 9 over the opposite, which was 2x. Is that okay? And then what would the cotangent be with this picture? 3 over 2x, very good. And again, if you are so inclined and want to write that as a single fraction, more power to you. There's really nothing to be gained too much by doing so. It certainly doesn't clean it up very much. But it is the only cleanup that could be done. So if you'd like to, go for it. If you don't want to, it's okay with me. I'm not sure what WebAssign will make you do. It'll probably make you put it over the same value. It seems to like that. Okay. Let us take a look then at one other piece of information in this section. I'm trying to find a clock since that one's not working. It's almost right. Yeah, it's actually about an hour off at this point, but
No, it doesn't work anymore.
it's not working. Yeah, it did work, I think, yesterday. So you know, just yesterday. It is right 2 times a day. Okay, so one other piece of information. We've got some special integration formulas. So these are fantastic. They're in your notes, right? I didn't make you write them down this time because they're awfully ugly, and I don't want you to transcribe them incorrectly because they are ugly. We have 3 special integration formulas. One is a squared minus u squared du. One is u squared minus a squared du, and the other one is u squared plus a squared du, and they should all look awfully familiar. Why do these look familiar? Huh? We just derived them, didn't we? And we didn't actually go through the whole derivation, but we went through the relationships and getting them, and then we did a couple of examples where we found them out sort of by hand, right? So if you get to your test and I'm telling you you can use the special integration formulas or that you can use any method you want, then you're welcome to use these. But if I tell you to use trigonometric substitution, then you need to use trigonometric substitution that we just did on those 2 examples. Is everybody with me? So be really careful when you're doing your WebAssign homework that you actually do some of them with some trig substitution so that you're not getting to the test and feeling like I haven't had enough time to practice and know what I'm doing on this problem. Okay? All right, so let's do an example. This one should look familiar. It almost looks like the last one we just did, right? Not identical, but awfully close. This one says use special integration formulas to integrate. I've got the square root of 9 plus 16x squared. Could we do this with trigonometric substitution? Yeah, it looks like the second one, the one we just did, right? The one where we ended up with the tangent involved. And we've got this because we've got the square root of the two values that are squared. So in order to use this, we do need to identify which pieces are what. In other words, when we looked at this before, we talked about the fact that this is basically identifying that I have an a squared plus a u squared du, right? And I need to figure out what is my a and what is my u, and I'm going to probably have to also identify what's a du since I'm not actually going through the substitution and I'm going through a special formula. So what is the a in our problem? 3. What is our u? 4x. And what we want to notice is that when the du is involved here, what do I get? And do I have a 4 in this problem present? No. So when I actually make the substitution for the dx, I need to be careful that I am going to, in fact, have a 1/4 in my problem. Okay? It's going to happen. Okay, so I'm sorry you're going to have to be flipping back and forth, but so will I. My formula there is the third one on this list of special integration formulas, right? This one right here at the bottom. U squared plus a squared. And what it says I need to do is I need to have a 1/2. Like the thing is, well, let me just tell you, the thing is that this is like cheating because we're not actually integrating. All we're doing is using a formula to plug in the results, correct? Do you guys see that? Okay. So as we're taking a look at this, we're jumping straight to the answer. The answer should be a 1/2. It will have a u in it. What is our u? 4x. It will have the square root of our u squared plus a squared. That's the 16x squared plus 9, or 9 plus 16x squared, plus a squared, which is our 9. The natural log of u, which is 4x, plus the same radical, right? We're using the same radical throughout, 16x squared plus 9. Close the absolute values, close the parenthesis, plus c. And I feel like I'm missing something. Yeah, I got to have that 1/4, right? So at the very beginning, I'm going to introduce a 1/4 out here, and I'll add a bracket right there before the plus c. All that's left to do is to clean up the pieces that can be cleaned up. And there's not a whole lot that can be, but there's a little bit. Obviously, we get a 1/8, right? And that 1/8 can be distributed through. So this 1/8 will distribute to the 4x, and it will distribute to the 9. So what is 1/8 times the 4x going to give me? What is it? I think you said it right. X over 2? Yep. X over 2. I've got my radical of 16x squared plus 9. And I have 9 times the 1/8, so that's going to give me 9/8 times the natural log of 4x plus the square root of 16x squared plus 9 plus c. So the formula is not cheating, but it's certainly really not calculus, right? And you didn't do any calculus techniques. You did some sort of an algebra technique of plugging a number in. I guess technically you did one calculus step. Do you know where it was? Yeah, the du at the bottom, right? I guess technically it was there. Du is 40x. You did do one small calculus step. All right, so this is it for section 8.4.